This is a very basic explanation for those who want to have a brief idea of what power factor is in electricity without getting into complex formulas. It is called power because it determines the true power that a circuit is consuming. It is called a factor because it is a figure that must be multiplied by something else. The power factor is a figure between 0 and 1. When a device is plugged in at a small or large industry, a certain amount of power is used. Basically, there are three types of loads that can be plugged to the electric current supplied by the power company. Resistive load, made up of resistors, such as those in an electric stove or oven or melting pot, an incandescent light bulb, etc. Appliances intended to generate heat or light by heating. Inductive load, made from coils of copper wire, such as those used in motors, transformers, electromagnets, etc. Capacitive load, made up of capacitors, containing metal plates insulated from each other and which can store small amounts of electrical energy in them. Let's quickly analyze these three types of loads by using a battery, a voltmeter, and an ammeter. The graphs in this example are not precise. They merely illustrate the process. Remember that any battery has some internal resistance, as shown here, and in case of an excessive current, it causes the output voltage of the battery to drop, even to 0. We use a switch to connect and disconnect the power source, in this case the battery. And at the output of the power source we connect our voltmeter in parallel and our ammeter in series. The full voltage produced by the power source is read at the voltmeter, and all current flow is shown by the ammeter. Now we add a resistive load to the power source. We will also illustrate our explanation with these simple graphs, which show us the readings of the voltmeter and the ammeter at a given time. For simplicity, we use square waves here. We turn on the switch and the voltmeter instantly reads the 12 volts coming from the battery. At the same time, the ammeter reads the current flowing through the resistance. Let's suppose that the resistance value is such that whenever 12 volts are applied, 10 amps will flow. To calculate the power present in our circuit, we multiply the voltage of the battery times the current flowing in the circuit. 12 volts multiplied by 10 amps gives us 120 watts. Keep in mind that in order to calculate the watts in this way, it is necessary that the current and the voltage are turned on and off at the same time. In the case of a purely resistive load, it is said that the power factor has a value of 1. If the current either lags or leads the voltage, the power factor goes low, even as low as 0. For a resistive load, the calculation for the power would be 12 volts multiplied by 10 amps multiplied by a power factor of 1. The result would be 12 times 10 times 1, 120 watts. Now suppose we turn off the switch and replace the resistive load with an inductive load, which in this case is a copper coil around an iron core. An inductive load is kind of odd. When turning on the switch and applying the voltage, the coil at first opposes the current flow, and after a fraction of a second the current flows freely. On the other hand, if we now turn the switch off, the inductive load tries to keep the current going, and even a spark jumps between the contacts of the switch. This is something similar to some sort of electrical inertia, as when we push our car. At first, we can hardly move it, but after some time, we can easily push it. If we now want to make it stop, the car will take some time to come to a stop. An inductive load behaves very much the same way. When first turning the switch on, at time t1, the full battery voltage will appear at the ends of the copper winding, but the current will take a fraction of a second to start flowing at time t2. This phenomenon is called current lag. Since the current lags the voltage and is not present at the same time, we can assume the power factor for an inductive load to be close to zero. We turn the switch off again and replace the inductive load with a capacitive load. Remember that a capacitive load stores a small amount of electricity as if it were a reservoir. The emptier the tank is, the more current is needed as the voltage builds up. Now we turn the switch on again. A capacitive load takes up a lot of current before its reservoir is full. Therefore, when turning on the switch at time t1, the current is so intense that the voltage is sort of short-circuited and it drops to zero. A fraction of a second later, at time t3, the capacitive load no longer allows more current to flow. We see that the current is leading the voltage. This is called current lead. Because the current is being applied without any voltage in the load, there is only power consumption when the load is getting both voltage and current, as shown at time t2. Since the current and the voltage are not simultaneous, we can assume that the power factor for a capacitive load is also close to zero. This was just an analogy. The true importance of the current leading or lagging the voltage becomes evident in alternating current circuits. What is an alternating current? Alternating current does not flow one way, as current produced by batteries, but it goes one way first, then stops, and flows the other way. It is as if we were switching the voltage polarity very fast. In fact, it does this 50 or 60 times per second. This can be represented in a graph like this. The red line represents the voltage and the black line represents the current. Let's look again at our circuit, this time using an alternator instead of a battery. If we plug in a resistive load, both the current and the voltage remain simultaneous. In this case, the power factor would be 1, so if we had 12 volts again, in this case alternating current, as our energy source, we multiply 12 volts times 10 amps times the power factor of 1, we would still have 120 watts alternating current power, just like we did in our direct current previous example. If we now replace the resistive load by an inductive load, things change dramatically. Since now the current lags the voltage by almost 1/4 of a cycle in a practical circuit. With this, the power factor goes down to almost zero, say 0.02, with which we would have 12 volts multiplied by 10 amps multiplied by the power factor of 0.02, we would have a power of 2.4 watts. A low power factor due to an inductive load causes problems since it overloads the power company lines, and penalties are charged on industrial users for working under those conditions. Going on with this example, if we now replace the inductive load with a capacitive load, the current leads the voltage by almost 90 degrees. In fact, the way to get rid of low power factor in industry is to use capacitive loads, also called capacitor banks, which make the current lead the voltage in order to compensate for low power factor caused by inductive loads. For example, if a factory uses many electric motors and transformers in their processes, a capacitor bank designed by experts can be installed so that the current leads the voltage just enough to compensate for low power factor. While it is difficult to achieve an ideal power factor of 1, a close to ideal figure can be achieved. Summarizing, Inductive loads make the current lag the voltage, producing a power factor close to zero, which is not good for the power company since it overloads its lines. Capacitive loads make the current lead the voltage, so a capacitor bank can compensate for the current lag, thus raising the power factor, which is good. Resistive loads do not make the current lag nor lead, so they do not require any compensation. I hope this information has been useful to you. Thanks for watching and please subscribe to my channel. Chava Tarin.